All right, guys. Hello, welcome to midterm 2 review. I'm trying out a new setup. I'll try to look at the lens, which is over here. It's a webcam, but I will look at the screen because that's what I'm seeing too. Anyway, midterm 2 review. We're going to be going over a few concepts. I've been informed that like the optics stuff is not going to be on this yet. So correct me if I'm wrong, but my most recent informant told me that. So yeah, everything else is fair game, obviously. We're going to go over the kind of 5 big types, and then specifically for a few of those, we're going to do like the multiple types the question can be asked. I'm going to be very careful here to define my right-hand rules and what I'm doing when, but at any moment, in case you see me like do it in my head or like quickly just do my like fingers against the blackboard and you want me to explain or talk about what tipped me off to use that certain method, please speak up, because I sometimes just go without thinking. People in the Zoom, please speak up if you have any questions. I'm sure there's other people with them, but I guess without further ado, let's just dive right into it. Okay, so I'm looking at again exam 2 review worksheet number 1, where we have these 3 infinitely long parallel wires. They're all carrying different currents in the direction shown, and they have a separation of d between each one of them. Also here, they gave us a coordinate system and the direction gravity is acting here. So it's going to kind of inform latter parts of this question. So I first want to just define like what I know. I1 equals 200 amps, I2 equals 400, I3 600, and that distance d is 0.12 meters. All right, so I think kind of the most important part here is just kind of addressing A, because if you can do this, the rest of it is like 135A, forces, arrows type questions. So I'm just going to start by drawing it out so I can see. The worksheet's posted on the class Google Drive under the exam review worksheets. All right. So those watching, I thank for your patience as I live write this stuff in real time. Okay. Okay. All right, and we have that right there. All right, I think we're good to go on the setup here. All right, so the first thing I just want to reiterate is that a current going through a wire will create a magnetic field kind of in a circle of the wire. So imagine like the wire is going through a ring, and that ring itself is a created magnetic field, right? So the way to kind of trace that magnetic field, because remember, it's in a 3D space, it's like it's circular, right? We can use a right-hand rule with our thumb and our finger curl. So this is, I don't know, like however you want to remember, I just remember it's like the thumb finger curl method. So let's just start looking at this current one, because it's going to have the same direction for everything underneath, right? So I'm going to first put my thumb in the direction. Oh yeah, okay. So I guess it's not mirrored for you guys. Yeah, okay. I'm going to put my thumb in the direction the current's going. So in respect to I1, it's going leftward, right? It's going this way. My fingers will then curl, and then we're on the opposite side, right? So up here on top of I1 in this area, we're gonna have a field going into the page. However, beneath I1, the field's going to be going out of the page. So to kind of remember that, I'm going to draw these. I'm just going to draw these little dots right here. It separates it, and I have B1. Sorry, I'm going to erase this coordinate system. It's not that important, but just so you know. So that field by B1 is going out of the page. And this applies to both the effect on I2 and I3, because they're both, on this side, right? They're both on this side of what I define as that dotted line. But everything above that dotted line, obviously, it's going to be going in. This is coming out. All right, so now let's look at I2. So I2 is kind of the tricky one because obviously, depending on which wire we're talking about, that being this one or this one, the field directionality is different. You can flip. So I2 in respect to I1, I2, sorry, I'm going to have to make myself easy to see here. I2 in respect to I1, thumb in direction, fingers point outward, right? Fingers point outward. So I'm going to call that, so B2, and I'm just going to call it A, just because A and B. Remember, the A part is in respect to above this dotted line, and the B part, as to be defined, will be below. Again, we're going to put our thumb in the same direction to observe below this dotted line. Our fingers curl inwards. Fingers curl inwards. So that means B2, B. Right? So there's a magnetic field on both sides of this, induced by this current. Above, it's going to be going out, and below, it's going to be going in. Okay? And the final one is I3. So again, I'm going to draw this dotted line to define both sides. Put my finger in the direction, and we'll see that above I3 is going to be going out of the page also. So I'm going to call that B3, right? And the reason why I don't worry about on this side and on this side is because there's no more wires here. So I don't need to worry about the magnetic field effect on the other. Because if you already have a good intuition, you know how this is going to go. It's going to be the effect, like we're looking for some force caused by these wires. So some magnetic force caused by these wires. The only places where the wires will be affected, let's just talk about this current 3 here, are 2 and 1, right? So we only have to worry about everything that's on this side. And then like with I2, we have to worry about both sides because I2 will have an effect on I3 and then on I1, hence their the A and B. And then same as I3, I1 will have an effect on all these guys, except it's only going to be going out of the page. So we only want to worry about this part, right? Cool. So we now have strongly established all of our directions of the B field. We're going to now use a different right-hand rule. And this right-hand rule is like the more traditional one, where we have our index finger in the direction of the current. I'm going to use I1 as my I3 as my reference when I discuss this. So I'm going to have my index finger, pointer finger in the direction of current, my middle finger in the direction of B. So for now, just remember that there's multiple B's here, right? And our thumb will be the force, right? Okay. So now, starting with I3, let's look at the effect of I1 and I2 on I3 per their produced magnetic fields. So stick with me. Let's first worry about the effect of I1 on I3. All right. So we do finger in the direction of the finger in the direction of the current. I was like, let me just double check, make sure I got this. Yeah, okay. So yeah, right, yeah. Finger in the direction of current, so I3 is pointing this way. Middle finger in the direction of the field. By I1, it's pointing out, so pointing out of the blackboard. And you can see my thumb's pointing straight down, right? All right, so we know the force on I3 by I1 is pointing straight down. Next, let's look at the effect of I2 and on I3. And then obviously we're not going to worry about I3 on I3 because, that doesn't make sense. So middle finger in the direction. What's the effect of I2? What's the field of I2 here? Here we're going in, so our thumb pointing up. Therefore, that's the force by this I2 on I3. All right. Sorry, I don't know if people are in the waiting room, or maybe someone just left. I can't tell. Whatever. Now we're looking at I2. So for I2, we need to look at the effect of I1 and I3 on I2. So pointer finger in the direction of I2, middle finger in the direction of the field of I1 on I2, so that's outward, and thumb points in the direction of the force. So you can see F1 points down. And also, like, as you expect, these guys are the same, right? Because the field's still the same direction and the currents are the same direction. Next, we're going to be looking at the effect of I3 on I2. Finger in the direction of I2, middle finger in the direction of the field by I3 out of the page, and thumb in the direction of the force downward again. Finally, we're going to be looking at the effect of I2 and I3 on I1, right? So I'm going to go to this side now because my pointer finger is this way. Pointer finger this way. Let's first start by looking at I3. Here the field is pointing out. So finger in the direction of current, middle finger coming out of the page, thumb pointing straight up. So that's the force I3. And then obviously it's going to be the same, right? Because we're going to have the direction of the current, the field by I2, but we're going to be looking at A because now we're on this side of it, right? We're on the upper side. Before we looked at B, we're looking at A. Coming out, again, we're pointing up. So do we all agree thus far? This is kind of the hard part. So yeah, this vector is for force 3 and force 2. Both of them are pointing up. All right, so I'm going to assume that we're all in agreement here. So next we're going to do part A. Now we have enough to do part A. Whereas which of these currents will be suspended, right? So the answer to that is just whichever ones have this upward, a force pointing upward, right? Because we have gravity acting here. We know I3 is just going to go down, but this I3 and this I1, these two wires right here, have these upward forces. So we know that it will be wires 1-3. Okay. So now we're asked in part B, for the wires that can be suspended, what must the mass per unit length of each wire be? So mass per unit length, that's always like, for me, I remember it was always getting kind of tripped up about that. But basically, it's a force equation with their relative lengths represented beneath them. So I'm going to write that out here. Is part B. So that's part B right here. We're going to first look at wire 1, and we're going to set up our equations here. That's the force of gravity per unit length, and the affecting forces acting on here. We have both, in respect to wire 1, we have both F3 and F2 pointing straight upwards. So, and that's in agreement with our coordinate system. So that's our expression. Okay. At this point, we just need to express each of these forces. So if you remember from last semester, our force of gravity here, mass times that G constant over L. I'm going to need to go on my knees here. So, oh, damn it. And now I like messed up everything because I like drew where I can. Oh God. All right, pausing the recording. And we're back. I'm so sorry about that. Thank you. The people who are in the Zoom right now, you guys have the real patience. I owe you one, all of you guys. All right, so here's our force expression. Like we said, we expressed that force of gravity right here, and now we're going to express the force, these magnetic forces produced by these wires, right? So what's our equation for that? It's going to be that mu naught, and then it's going to be the current we are like in reference to. So like in the case of force 2 on I1, that's always going to be I1, right? So the current we're in reference to, and then the other current that's inducing the magnetic field on it, right? Or whose magnetic field is affecting it. So that I like to think about it like this is the current of the wire we're talking about, and this is the current whose magnetic field is affecting this guy. And that's going to both be divided by 2 pi and that distance between them, right? Yeah. And then since our forces are in the same direction, we're going to be adding here. Same thing. So we're going to do that mu naught. Except for now we're talking about, oh, sorry, this should be I2 here. Now we're talking about I3. The distance between I1 and I3 is just 2d, right? All right. At this point, remember what we're looking for here is we're looking for a mass per unit length. So what this expression is almost perfect, except we have this gravity value right here. So if we divide both sides by gravity, instead of rewriting, I'm just going to erase here. We divide both sides by gravity. So 1 over g. We now can find an expression for that mass per unit length. So here, what I recommend you do if this were the exam is you're going to want to factor out mu naught and I1 because those are constant and 2 pi. So you'll have, I'll do it for this first one actually. Mu naught I1 over 2 pi g, right? Because that g is going to be multiplied, 1 over g is going to be multiplied on both of them there. And oh, and d actually, d can come out too. So what we're left with now is just I2 plus I3 over 2. Remember, because I3 was 2d away. There was 2 d's between them. Okay, so at this point you have enough to plug in everything. If you do that, your answer will come out as 0.0238 kilograms and then per meter, because we're talking about a force per unit length. So yeah, that's kilograms per meter are the units. And that's your force per unit per length in respect to wire 1. So just to make room, I'm going to erase this guy right here, and I'm going to do the same thing again, except this time we're going to be talking about wire 3, the other suspended wire. All right. So essentially the same setup here, you know, with mg over L, which equals mu naught, the wire we're talking about. In this case, it's I3, the affecting current over 2 pi and their distance. The only difference is in the case for wire 3, we have the forces in opposite directions, where you know F2 points up and F1 points down. So our coordinate system defined F2 as positive. So yeah, that's why we did that. And then F1 here is, you know, mu naught. Again, we're talking about I3, I1 divided by 2 pi 2d. Okay, and this is completely the same setup as the previous one. You know, multiply by 1 over g on this side, factor out, then solve for a mass per unit length. I'm just going to skip a few steps here, and I'm just going to give you the factored form. So it's going to be mu naught I3 2 pi dg, and then now we over here we have what's this, I2, right? Yeah, I2 minus what was that? Oh, I1, yeah. So I1 over 2. Okay, so at this point we have enough to solve. Just plug in everything, and this will come out as 0.0306 kilograms. All right.
I have a quick question.
Yeah.
For the left side of the expression we derived, why is it only 2 pi d instead of 2 pi 2d between I1 and I3?
Between I1?
Yeah.
I3. Oh, I'm sorry. I flipped. You're right. That's right. So this is I1 here. No, wait.
I think, yeah, it's I1 there. Yeah.
There we go.
And then, yeah, okay. And then can you explain for part A why it's not, like why it's also wire 3? I thought that gravity would just oppose wire 1, so it'd cancel out, but the other one would still potentially go down because there's like force 1 and 2 are acting in opposition of each other.
Yeah, okay. So that's a good point here. If we look at the actual expression, remember it's that mu naught constant Okay, that's constant. Let's just not even worry about it. And this 2 pi is also constant. Now let's look at what's not constant. That's going to be this portion of the expression, right? Per the fact that I2 is only a unit d away instead of with I1 is 2d, smaller number here means bigger number overall, right? So that means the force by 2 is going to be invariably greater than 1 and can thereby like push it up.
Okay, so then how do we know that the force of gravity would, I guess, like equal whatever magnitude is of the force vector of like F2 minus F1?
How do we know that? So you're basically saying like, how do we know that these wires will be able to even be suspended, like because of gravity present?
Yeah.
So we're dividing by that G value here. So let me try and think about that for a second. How should I say this? This is on the midterm 2 review worksheet. Okay, so what we are looking for by dividing this 1 over G is the mass that the mass per unit length the wire must be for it to be able to be suspended. We are solving for what the mass per unit length must be such that this gravity will not be able to bring it down. If this was 0.031, at that point, this would be too heavy and the wire would go down. So this value right here represents what it needs to be such that it could be suspended. That's what we're solving for.
Sorry, I guess I should rephrase my question. I was asking like how we knew the answer for part A was 1 and 3 based off of what we knew at that point.
Okay, yeah, I guess like if we're getting into the weeds here, you make the assumption that it's going to be corrected like this. So I guess I should have said maybe in part A, like given conditions where the wire, I don't really know how to answer that. It's just that the force is pointing up, it could, and then we end up proving that it could. Like here, we're basically saying like what could be suspended. It could be wires 1 and 3, and here we're proving that's possible. Does that answer the question?
A little bit. I guess like when I did this question, I just put I3 because it had some upward component and some downward component. And so in my mind, I was like, okay, the one that would be suspended would be the one that has no net force acting upon it, as in like something is canceling out.
Okay, so you mean you put I1?
I put I1. I don't understand why I3 is also there.
Yeah, okay. So that's like a great intuition that you had that to begin with. But the reality is there would be like per the fact that there is some force pointing up and we do not know the mass at that time, there is a possibility that one could be suspended as well. Right?
Okay.
Yeah. And then we found that there's a mass that actually does correlate with that. I guess the more important thing to ask yourself if you were solving this is which one could never be suspended, and that would be I2, right? Because it has no force vector pointing up.
Yeah, they're both going downwards.
Exactly. So yeah, if there's that pointing up one and like the mass is like reasonable, you can think about it like that.
Thank you.
Yeah, okay. Sorry about that. I kind of got in the weeds there.
What worksheet is this problem on?
This is on the exam 2 review worksheet.
Okay, thank you.
It's number 1. Okay, so that's cool. That's number 1. Here we go. Number 2. You guys have access to this worksheet, right? It's the second person.
Yeah, we have access. I didn't know that there was an exam review 2 worksheet.
Oh, my bad. Should be there. Yeah, I have a separate file for the exam review ones. I was like, should I do that? Now maybe I realize I shouldn't have because it's just confusing. All right. All right, so now we're going to be looking at number 2 here. So here we have three long parallel conductors and each carry a current of 5 amps as shown in that diagram. Each has a current coming out of the page, and that distance A between every single one of them is 10 centimeters, okay? In part A, we're asked to find the magnitude and direction of the magnetic field at B, and then magnetic field of direction at point C. So I'm going to draw the whole diagram first. I'll just pause the recording so people watching at home don't have to watch that. All right, we're back. So here's our diagram. Every single one of these currents is 5 amps, right? So this one, we're asked to find a magnetic field produced at certain locations. So this is, again, a different right-hand rule. And personally, this is my favorite one. And it's initially complicated until you establish like its guiding principle. And that being the perpendicular nature of the produced vector. But let me explain that through example. So here we're going to talk about point B. Point B is right here, right there in the center, right? I'm going to draw it, another diagram of it right here. Point B, right here. All right. So for this right-hand rule, what we're going to need to do is put our thumb in the direction of current and our fingers curl such that the produced vector is perpendicular to the shortest distance between the current and the point. All right, that was like a lot of words for me to say this. You put your thumb in the direction. In this case, they're all coming out, so my thumb's gonna be pointing out every single time. And then my fingers curl where the produced vector is perpendicular to the shortest distance between them. So I apologize, like this doesn't look great here, what I'm doing, but essentially what I have is a thumb pointing out, my fingers are pointing this way, So this vector right here, this vector of the, B by P is pointing this way. And what I said is it's perpendicular to the shortest distance. So if we apply that vector right here, right? That's what that little line is right here. We see that this vector is perpendicular to the shortest distance, which is a straight line between them. So from P to B, that's the shortest distance. The produced vector is a straight line. Does that make sense? I hope so, because I don't want to, I won't be so repetitive every single time, but just to establish that, it's going to need to be perpendicular because it's confusing, right? Like you're like, oh, my fingers are curling. So is it like slightly up, down? No, perpendicular vector. Now let's look at the effect of N on that B. Again, thumb in the direction of current, fingers like this, such that they're perpendicular to the shortest distance between them. My B vector by N, I'm sorry, magnetic field by N, N position is left. Okay. Next, we're going to be looking at M. Again, thumb in the direction of current, and our fingers curl such that it's perpendicular to the shortest distance between them. So straight line, and then perpendicular is just downwards. All right. So essentially what we have to solve for here is, some net magnetic field, right? But if you have a good eye and good intuition, you know that with recognition of what the equation is, right? It's like mu naught the current 2 pi, and then that distance between them, right? So it'd be A. We know that this is constant. The distance between N and B and P and B are both A, so that is constant between them. And then their currents are the same, right? So the fact that the vectors point opposite directions tell me they cancel out. So that means the net component, the net magnetic field at B by N, M, and P is just this guy right here. Or it's the only one we're worried about. Because of that, I'm going to define my coordinate system such that it's positive. I like to work with the positive value. It's easier for me. And we just have to plug in everything. So I'm going to call that the magnetic field at B. It's just equal to that y component of Bm, where it happens to only be in the y direction. So it's just, that mu naught constant, 4 pi times 10 to the minus 7, times its current. They're all the same. They're all 5, divided by 2 pi times 2a, right? Because m is 1a, 2a away from b. You plug everything in here, we're going to get 5 times 10 to the minus 6 t. And, when you have direction, it's going down, right? We already explained why it's going down. Cool. So the next part is basically an expansion on this. I'm going to go ahead and erase what we're looking at here. Also, if you guys feel like I'm taking too long, I can speed up. And if you guys don't need explanations, let me know and I'll speed it up. I don't know where we're all at here. I figure it's better to just be overly thorough than underly thorough, right? Okay, same setup here, except now we're looking at this point, point C, right, which is right there. Oh, that's confusing. I shouldn't do that. We're looking at this point C. Point C. So we're going to again do that right-hand rule where thumb in direction of current, and then the field that's perpendicular to the shortest distance. Let's just first start out with P like we did last time. I'm going to call this my C position right here. All right. So starting with P at C, thumb in the direction, fingers curl such that it's perpendicular to the shortest distance. So like right here, perpendicular by P would be a vector pointing that way. So that means B, P. And by definition of it being perpendicular, right, we're gonna have a 45, wait. Okay. Yeah, we're gonna have a 45-degree angle right here, right? Next, let's look at N. Again, thumb in the direction of the current, fingers perpendicular to the shortest distance. It's going to be going up like this. So this is B, N. All right. Next, we're going to look at this the effect of point M. Thumb, fingers perpendicular to the shortest distance, pointing straight down. Let's call that B, N. All right. Again, let's express this through its, this is moving in two directions, right? Like relative to our coordinate system. So that means we need to break it into its respective components here. Again, a good eye tells you that these x components are going to cancel out for the previously explained reason. So what we're left with is, I'm going to call it bx equals to 0. So all we really want to worry about is that by. Our by is going to be what encompasses that magnetic field here. Okay. So I'm going to call that B at C equals Bn, its y component, plus Bp, its y component. Remember, both of these guys have both of their components are on the same line right here, pointing straight up. In agreement with our coordinate system, as that means they're both plus, minus Bm, which is pointing straight down. Okay. Here, we can also further clarify this because we know that, looking at our equation again, mu naught I 2 pi a. For these guys, they're both a distance a away from that C position, and they both have the same current. So I'm just going to call it 2b n y. Oh, wait, not a. That would be Pythag root 2a, right? Yeah, root 2a. No, I didn't. But yeah, so the distance between them is not a. Please be careful. It's a root 2a, right? So we're going to use Pythag. So root 2a. That's from P to point C and from N to point C. All right. So I can write it like that, minus Bm, and the Bm is the same as before, except now it's just the distance a away. So let's express. Let me scoot over actually. But I'm going to get on my knees real quick here. So equals to 2 mu naught, and then all the currents are the same here. Cosine that angle theta, which is 45, divided by 2 pi root 2 times a, and then that's going to be minus mu naught I 2 pi a. In this case, m is only a distance away from C. Here you have everything you can plug in. In fact, you can factor out a mu naught, an I, a 2 pi, and an a. And oh, actually, let me do that factoring for you because I want to show you guys something. All right, so let's do some factoring. So we're going to factor out the mu, and this is just continuation from up here. So stay with me, guys. So mu naught over I 2 pi a. What are we left with on this side? 2 cosine 45 divided by root 2 minus 1. And this actually comes out as, it's going to be root 2 over 2, so 1 minus 1 equals 0. Therefore, everything, like that means this guy becomes 0, right? And then anything times 0 equals 0. So that means the net magnetic field at C is actually equal to 0. All right. And then this is just a proof you would do by plugging into your calculator and seeing that. Okay. So in reality, like if we think about what that means over here is these two guys pointing straight up counteract this BM pointing down here. So the y components of BP and BN counteract BM, which is pointing down. Whew. All right. I'd love to take a drink of water. Oh, go ahead.
Can you quickly re-explain? So is that superscript a 0? And that or the arrow?
This whole thing cancels out to 0 because 2 cosine 45 is equal to root 2 divided by root 2 equals 1. 1 minus 1 equals 0.
Got it. Okay. Thank you. That makes sense.
Oh, looks like there's something in the chat here. What's the answer to 2a? Okay, answer to 2a is 5 times 10 to the minus 6 t downwards. All right. Yeah, I was saying, I would love to take a drink of water, but the webcam's set up on the water right now. I'm gonna be so dehydrated. I'm like breathing all this chalk. If I go down, somebody call USC protecting services there. Call DPS. Next question. Oh, these ones are good too. So yeah, there's definitely going to be something like this. And if you remember from session, I told you once you see like a rod or like a loop in a rectangular square, you got to think that induced voltage B length times volume, length times velocity equation. But anyway, before we get into that, let me just go over some stuff here. So we have to recall that induced voltage results from 3 different things, and likely a combination of these 3 different things. So first being a change in B, right? Next being a change in area, and the other one is like a change in orientation. So if your loop's like this, it goes like that, right? With a field going through it, right? Obviously, there has to be the field going through it. And what we'll more often see is an area of a loop changing, or the actual change in the field. Like the orientation one is less common. So here, let's see, in our question, we have a rod, length 0.45 meters. It slides along there. There's 2 resistances, R1, 4, and R2, 8 ohms. They're connected on both ends of the loop. There we go. Magnetic, constant magnetic field going into the page, and then an external agent is going to be pulling it to the left there with a constant speed there. Okay, so the first thing we're asked to find is the magnitude of the induced currents through each of the resistors. So, like I said, over here we're looking at a situation wherein we have a rod moving through this rectangular square thing. So we got to think this equation. This is going to be what we're working with here. All right, and that little v here is going to be in reference to how fast it's being pulled. I'll try to remember to write voltage is a large V. Little v is velocity, at least in these situations. Guys, you're supposed to tell me if I'm writing out of frame. Or maybe I'm not actually. Maybe my Windows is covering it. Oh, no. I'm kidding. God. I embarrass myself for 2 hours on every single exam review session. So here we can plug in everything. Everything is given. Times that length, which was 0.45 meters times 6. Sweet. So that comes out as 12.5 volts. All right. So we're not asked for the induced voltage, we're asked for induced currents. But to find that induced,
It's at 12.15 volts.
I'm sorry?
12.15 volts.
Oh, did you plug it? Maybe I in my key I forgot it. You plug it into your calculator and that's what you got?
Yeah.
All right. Be advised, viewers, 12.15. Okay. So remember, we're gonna use like Ohm's law here. So V equals IR, or in the case of these induced guys, voltage induced, I induced, and basically the total resistance, right? We're gonna rearrange to find for this I induced relative to both cases. So that's gonna be I induced over R1, I induced R2. Okay. Oh yeah, so I actually wrote it as 12.15 in later steps, but I forgot to write it like that there. Thank you to whoever called that one out though. Okay. And then, just simple plug and chug here, right? Just plugging in both of their two resistors here. 1.5. All right, so now we have an induced currents on each one. The next thing we're asked in part B is what is the direction? What direction is the current flowing through the rod? Okay, so again, this is a right-hand rule here. We're gonna do pointer finger. I'm not gonna redraw it because this one's pretty elaborate here, but work with me on your end, and I'll be doing it towards the screen, so it's as if my hand is with you here. Pointer finger in the direction of B, thumb in the direction it's moving, and your middle finger, wait a minute. Okay, that's right. Okay, yeah. Pointer finger in the direction of B, thumb in the direction of the velocity, and your pointer finger or middle finger will point in the direction of the induced current. In this case, that means the induced current is going down, right? Pointer, thumb, middle finger. Gotcha. So down. For part B, down.
So could you explain that one again?
Yeah. So we're going to do pointer finger in the direction of the B field. Here we're going into the page, right? Next thing we're going to do is thumb in the direction it's moving. So here the external force is pulling it to the left. My thumb's going to go to the left. Middle finger in the direction of the induced current. So,
Okay, so you can like switch them between force, current, and field as long as you like rotate them the right way. Like I thought it was always force was thumb.
There's four different right-hand rule equations. So here, we're not looking for a force. So we need to use one that represents velocity, right? Okay. So it's going to be the moving one, where our thumb is that our direction of the way it's moving. I think 2 worksheets ago, I wrote out all of the 4 ones with like the pointer finger this way, thumb this way. So in case you want to do that, and I wrote like when you'll use them, basically like, is it a point charge? Is it a wire? Is it this or that? So check that out. But yeah. So I say pointer finger direction of B, thumb direction of V, middle finger direction of I induced. All right. So now in part C here, we're asked calculate magnitude and direction of the external force required to keep the bar moving at a constant speed here. So that little word, there's the words right there, constant speed, inform a lot, right? Constant speed can only occur when there's no change in acceleration, therefore an external force that is balancing out the forces. There's no net change in force and no change, and thereby no change in acceleration by definition, right? So allow me to, flying. Remember these values, we're going to use them too in part C. Like I was saying, constant velocity tells us that the force external I'm going to call it force EX, needs to equal that magnetic force FB, which we previously explained was equal to the total currents that are there. So there's two different currents, remember, because there's the two different resistors. And that length times B. Okay. At this point, we can just plug in what we saw. We previously solved I induced 1 and I induced 2 as. So that was 3.04 plus 1.52. And that length we're given 0.45. And then the B 4.5. All that comes out as 9.23 newtons. We need to define a direction. So now we're going to be doing like a different right-hand rule, but we're going to be recognizing force, right? So we're going to do pointer finger in the direction of the field. We're going to do middle finger in the direction of the induced current. We've just established that as down. And our thumb will point in the direction of the force. So middle finger direction of B, going into the page. Restart that. Pointer finger in the direction of B, going into the page. Middle finger in the direction of I induced, which is going down. We previously proved that. And our thumb is going to be pointing in the direction the force will be, which is going to be leftwards. So left. So you can see that with these right-hand rules, you will often, you need to solve for, it's 3 unknowns, so you need 2 knowns, right? So we first had to find we knew we'd be looking for that force, right? But the only way to find that force is with knowing the direction of I induced. And the only way to know the direction of I induced is to use the right-hand rule where, pointer finger in the direction of B, middle finger in the direction of the I induced, and thumb in the direction it's moving, right?
Isn't that direction though that you get from the thumb the direction of the force that the magnetic field is putting on the bar?
Yeah, exactly. So I've now done both of those ones, right?
Right, but in that case, then the external force would have to be the opposite of that, right? Like my question, I guess, is you use this right-hand rule, and so you figure out that your thumb's going to the left. Isn't that thumb going to the left the direction of the force that the magnetic field is putting on the bar? In which case, the external force would have to be the opposite of that, which would be to the right to counteract it.
One second, let me think about that for a sec. Let me think about what you're saying. Yeah, okay. I get what you're saying. The thing is, we're in both cases, our middle finger is going to be pointing in the direction of the current, right? It is the induced current. So the actual magnetic force acting on that wire, like the current's not going to be going in that same direction. It's because that metal bar is moving, a current is moving through a magnetic field, a current is being induced on it. We need to establish the direction that current's going. We prove that it's going down that way, so therefore the force and the actual velocity are both in that same direction. Yeah.
Right. My point is,
I'm going to open the window, but I can hear you. It's like 90.
Okay. My point is the force, so the velocity is to the left, and it's moving through the magnetic field. I get that. And that induces a current. So then you have the current and it's going downwards. But when you use the right-hand rule to figure out the direction of the force that we just did, the current's going downward and the field is going into the page. So your thumb points to the left.
Yeah.
My point is, isn't that direction the direction that the magnetic field is inducing on the rod, like the direction of the force that the field is inducing on the rod? And in this case, the question is, what is the magnitude and direction of the external force required to keep the bar moving, which would have to be equal to but opposite the force that the magnetic field is now inducing on the bar?
Okay. I'm going to pause the recording because this is going to get complicated and it's unnecessary, and I don't want to All right, we're back. Well, I need to make a clarification that a student, Aiden, caught and he informed me of. So the question says the external force to keep the bar moving at a constant speed of 6 meters per second. So that external force, let me be clear, is not the initial force acted like that causes the bar to start moving, right? This bar won't move by itself. There is some force that gets it going. That's what I'm going to call F1. And I guess you'd say this is where I was getting confused. It is also an external force that is pointing leftwards, right? So, but that's not what we're solving for in part B, in part C here. What we're solving for is an added force, I'm going to call it F2, such that V remains a constant, remains constant, 6 meters per second. By definition of constant velocity, there is no change in acceleration. To achieve no change in acceleration, this F1 and F2 forces need to cancel out. So that's why when we solve for F2, its direction is rightwards. It's going to be opposing the direction this bar is moving through the system. So like TLDR, F1 is what gets this bar moving, and it causes that initial velocity. Without F2, that guy will keep getting to go faster. However, F2 is added such that it cancels out F1, such that V remains constant. All right. Done. The right-hand rules that we discussed still stand. Right? Because we can use the right-hand rule to find F1, and we know we need to find the opposite, which is F2. All right. Enough of question 3, man. All right. Oh, this one's actually pretty similar to this. So this next one is a pretty recent midterm question. This was on one of the midterms, so short but worthwhile. So here we have a side wire generator consists of a conducting rod with length 50 centimeters. It's free to slide. The entire circuit is immersed in constant uniform magnetic field pointing into the page with that given strength. The wire is pulled to the right with a constant velocity of 2 meters per second. There's going to be some force there. We just discussed that. And EMF is induced. The circuit has a total resistance of 2 ohms. So part A here, at which point of the rod A or B is there higher potential? So I'm going to draw this guy out first. Oh, this is very similar to what we were just talking about, actually. Okay. Where point A, B, C, D. All right. Okay, so as this wire moves, there's going to be more B into the page as this area gets bigger, right? It's going to be like, remember, there's like a whole bunch of these B guys right here, these B fields into the page. As this wire moves, there's going to be more B going into the page. So we need to oppose this, Lenz's law, right? So to do that, we need to have magnetic flux increasing coming out of the page. So that means within this area, I'm going to draw B induced, this flux right here, right? Now, if we do another right hand, I guess I need to solve for current first, right? Yeah, so we do another right hand rule, right? Where we're going to have current pointing, so B, how did I write it before? All right, so we're going to have the induced current pointing upwards, right? Velocity, thumb going into the page, middle finger going into the page, thumb pointing upwards. So we know that we're going to have an induced going up. So by that logic, we now have enough to solve for part A. I forgot that part A is asking for that, which has the higher potential, right? By definition of this current, the voltage drop between B and A is going to go this way as the current goes that way. So that means point B is going to be the position with the higher potential. So B. All right, sorry, I forgot that we had to answer that part. And now in part C, the part I was discussing, what direction does the current induced current flow here? So like I said, we're going to have more B going into the page. To oppose that, we're going to want to have more B going out of the page. That means the B induced is going out of the page. We set up our right-hand rule where our current's pointing up and our fingers curl towards the B induced. So that means it's coming out. It's only possible when your thumb pointing like this, right? Because it was the other way it'd be going in. So thumb pointing out. So I induced going upwards. Therefore, as applied in this circle here, it's this rectangle, it's counterclockwise. Nice. Part C, we're asked, what is the induced EMF? So remember, whenever we see a rectangle that's rectangular square with a field that's changing, we know we're going to use this equation where everything here is given, right? So 0.5, 0.5, and 2. So that comes out as 0.5 volts. Next, part D, we're asked for that I induced. Again, we're going to set up Ohm's law, except we're looking for an I induced where EMF induced over that R total. That comes out as 0.5 over 2 equals 0.25 amps. Okay. And now what we were just talking about. So to get this V going, oh, I guess this one doesn't even ask for direction. All right, I'll solve for just the force value, and then I'll discuss the direction like we just talked about. So here, we're looking for the force such that constant velocity is maintained. Remember, to get this V moving, there's going to be some force. So I like to call it V by force 1, right? This is what gets the guy going. This is what gets the rod going, right? And to have a constant velocity, by definition, F net, no change in acceleration. Therefore, F net has to equal 0. So we're going to be looking for this F2 value. So F2, which is basically the magnetic force here, is going to be that I induced, which is the current acting through it, that length, and then V, right? That field. Plug in everything we just solved for. Right, and then if we did ask for the direction, we would say leftwards, because the external force added such that constant velocity is maintained is F2.
I actually think
Uh-oh.
I was wrong, but I think I was wrong because I think you mixed up your index and middle fingers for the right hand rule. Because I'm looking now on Khan Academy for the right hand rule of current through a rod or like a wire. Okay. And this would apply to both 3 and 4. You were right at first when you're trying to figure out the direction of the current induced. But once you know the direction of the current induced, then
is it the thumb one?
Then the right hand rule becomes your index finger is in the direction of the current and your middle finger is in the direction of the magnetic field. And then your thumb is the direction that the magnetic field now is inducing the force. Your thumb is in the direction of the force that the magnetic field is inducing. And on number 3, when you were going through it, you still used your, instead of your index finger being the direction of the current, you used your middle finger as the direction of the current.
Okay, so you're saying that our pointer finger is pointing down, right? Because I induce is going down. Middle finger in the direction of the field, and your thumb is in the direction of the force, right?
Right. In which case, the force
would be right.
Would be to the right. So,
but Aiden, I agree with what you're saying. That is true. But there's multiple ways. I used a different way of the same right hand rule, I think. Incorrect. Wait, shoot. One sec. Okay, now I got to really think about this.
because the current's going up. It's counter. The current's moving up.
Which we're talking about number 3. The current was going down, right?
Oh, okay, yeah. I was talking about number 4 briefly, but yeah, in number 3, the current's going down.
Okay.
So you have your pointer finger facing down, and then your middle finger facing into the page. So
And
the
your thumb
force.
points to the right.
So yes, so the force that the magnetic field is now inducing on the rod is to the right, in which case the external force to continue to like counteract that force is to the left. So
You're
C should
right.
actually
You're
be
right.
to the left. That's why.
Yeah.
That's where the confusion was.
That's why it was left.
Yes. So it should be the left for the same
Yeah.
reason I was saying, but yeah. And then in 4, it's the external force should be to the right.
Yeah. One second, let me write this one down. Oh, good Lord, man.
And the only reason we flipped those is because I think, if I remember correctly, you accidentally mixed up your pointer and middle finger when you were doing the right hand rule for part C in number 3.
So I see. So that's where the confusion came from.
Yes.
I used my pointer finger to point in the direction incorrectly. I incorrectly used my pointer finger to point in the direction of the field, when that should have been in the direction of the induced current, where then my middle finger would be in the direction of the magnetic field.
Right. Because the magnetic field wants to oppose the motion of the
Right.
rod.
Yeah, because like my lens is off. You're
Yeah.
absolutely correct. Yeah, that is absolutely correct. So I'm just gonna just briefly discuss 3, and then we'll move on to 4. So the reason that 3's force points, wait one second, leftwards, right? Yeah, is because the initial force here is pointing to the right. So the left opposes that right.
Or it's not, I don't think it's, I wouldn't imagine it as the initial force. I would visualize it as the force on the rod by the magnetic field.
Oh, yeah, you're right, because the other one is going to be the induced force. The force that by the induced magnetic field.
Right. Yes.
Right.
So like the way I visualize it is like you have a rod, you start pulling it to the left, and that's what gives it the 6 meters per second. And that's just like you're pulling it. But now that it's moving through a magnetic field, it now has an induced current. And so the magnetic field is now, because it has an induced current, pushing it on it with its own force. And that force opposes the motion that you were originally pulling it in. So that force in number 3 is to the right. So then the answer to C is to the left, because now you're trying to continue to oppose the force that the magnetic field is inducing on the rod.
Yeah, which would have been proving that I've been going to the right. All right, Aiden's correct. Aiden's the new SI leader. He is absolutely correct. People watching, please listen to what he just said. That was correct. And then I guess we should extend that same logic to number 4 here, where so what we're going to do here is a pointer in the direction of the current, middle finger with B, and like this, right? So that
so the force is to the left because it's trying to oppose the motion that
because
induced.
it's to the left. Yeah, there we go.
So then the external force would be to the right to maintain the velocity.
Wait, dude, I'm confusing myself. All right. Yeah. So it's to the right, because when we do our right hand rule here, the initial one is to the left, right? So to oppose that and maintain that F net equals 0, we're going to need to have this force acting to the right. So remember, the right hand rule we're going to be using in this situation is our pointer finger in direction of that current, our middle finger in the direction of B, and our thumb here in the direction of the force, and that's going to be the one induced by the moving rod. So that means to oppose that, we're going to need to have an equal and opposite force to the right. So that's correct. Yikes! That was a blunder right there. Oof. That's going to be confusing. All right. Whew. Gosh. Let's talk about number 5 now. So here we're going to have like this this power system where we're going to compare the situation in which it's strictly at 120 volts, and then the case a step up and step down are used. So essentially, what we're trying to prove here is like a change in power respective of which system being used. So what we're given is the power arrives at the town. I'm going to call that P town as 80 kilowatts through transmission lines. The resistance of the transmission lines are also given. So we want to find the power saved, so therefore the difference between the systems. If the voltage is stepped up from 120 volts to 300,000 volts, 30,000 volts, and then back to 120 versus just having it at 120 constantly. And we also get to assume here the transformers are 99% efficient. So you're going to basically solve this in 2 parts, like I said. First being when you're transmitting the power strictly at 120 volts, and then the power saved by using a step up and step down system here. So let's first just do number 1. So this is when we're transmitting strictly at 120. So when you first determine, when you first find a current such that we can plug it in to find a resistance, right? Because these resistor elements are going to be absorbing some of this power. So we're going to use P town, which is equal to the current, times V to solve for I, which is equal to P over V, right? Such that we can plug it into the power of the resistor equal to I squared R, right? So okay. So what we have here is here's something to plug in here. Given resistance, and it comes out as 8,880 watts. All right, so now to find that P total in this first scenario, we're just going to add those 2 together, or add the power of the town. Remember, that's 80 kilowatts plus what we just solved for, PR. We're going to do that, and that will come out to be
So that 8880 watts is the power through the resistor?
yeah.
Okay. Okay, thank you.
And that's the total in the case where we're only going to be using 120 volt system. Okay. So awesome. That's part 1. We're going to remember this. We're going to remember this number, and we're going to have to again use that when we want to find the difference between them. So just so I have enough space, I'm going to have to erase here. All right. So next we want to find the power saved by using step up and step down. So the power at the town, I'm going to call that P1 or P town. I'm going to say P town equals P1, right? We know that that's going to be equal to the power that's delivered after the second, after the step down, right? So that's going to be equal to EP2. Effectively, P2 then equals P town right. So P2 equals okay. So with P2, the current, like P2 is when our voltage is 30,000, right? 30,000 volts. So we can now find the current associated with P2, where P equals IV. So P2 equals I2 over V2, where V2 equals 30,000, P2 equals 80 wait, was it 80? Equals 80,808. Yeah, this guy. And we're just going to divide those guys. That equals 2.7 amps. So that's the current through the 30,000 volt system. At which point we can now find a resistor value here. All right. That comes out as and now we have enough to solve for P3. That being the power upon this upon the step up, right? Before it goes through the resistor, the power upon the step up. So that means from the 120 to the 30,000. So we'd have to sum those, right? So that being P3 equals this PR plus P2. That's that 80,808 plus 0.14, which equals, all right. Oh, wait, that's not. We need to first find that P of the generator, right? All right, so now we have upon step up. So now we can find the P generator, which is equal to, we call that P gen, which is equal to the P3 times 1 over 0.99. That's because it's going to be that through that 99% efficient transformer. And that's going to equal all right. So at this point, the final thing we need to do is find a change in power. We're going to be comparing the systems where this is what we got in part 1 of the question. Minus what we just solved for right here. And that equals 7,263 watts. All right. Pause recording quick, my computer's gonna die. All right, let's just do this RLC question. And this is our last one here. So this is question number 6. We have an RLC circuit with a resistor 300 ohms. We have an inductor here, a capacitor. We're given the VRMS value, and we are given the frequency, right? So the first thing we're asked for is determine the impedance. And like I said in the most recent worksheet, these questions are very much just the plug and chug game, right? So impedance is that's our Z variable. What's our equation for that? That's R squared plus XL minus XC squared. We don't know either of those guys right now. So let's first find XL. So XL is at 2 pi, the frequency times L. That comes out as 603. And then let's find XC here. So XC equals 1 over 2 pi FC, where that equals 198.94. Okay, so now we have enough to plug into the Z equation. R is already given. So therefore, we can say Z equals 300 squared plus 603 plus, or minus, sorry, minus 198 squared, square root this whole expression here, and that will come out as 503 ohms. And kind of remember, like, this impedance represents essentially everything in this system that could be opposing electron flow, right? So it's I like to think about it generally as like a total resistance, a value of total resistance. Okay, so next part B, remember this value, that's our impedance value. Part B, we're asked to find the IRMS. So IRMS expression, just like how we normally find these things in the situation, it's just equal to RMS over that impedance value Z, right? And in the case we're talking about, like, remember, like V max, this is not like related at all, but I mean, like, if they ask for like V max, remember that it's adjusted per an addition of root 2, where VRMS over root 2 equals V max. So let's say they were like, give me current max, you would have to plug in V max, right? Where Z equals R in that situation, because, you know, at the resonance frequency, Z equals R. That's like by definition. Okay. So VRMS is given 50. We just solved for that impedance value, 503, and that comes out as 0.099 amps. All right. Part C, phase angle. Again, plug and chug. C there, and we're going to have the inverse cosine of 50, 300 over that Z value, which is 503. That comes out to be 53 degrees. Okay. Whew. Almost done. Remember this RMS, the IRMS value, because we're going to use that in part D, wherein we're finding the voltage, what do they have it called here? The RMS values across each circuit element, right? So there's going to be one across the resistor, the inductor, and the capacitor. And their equations are essentially very similar here. I'm going to say V RMS resistor, V RMS inductor, V RMS capacitor. Okay. So every one of their expressions has that IRMS value. We'll just solve for that, remember. Times resistance times XL times XC. So we solve for this. This was given. Solve for this, solve for this, solve for this, solve for this. Plug in everything that we have. And what you'll get is 29.7 volts, 59.72 volts, and 19.7 volts. And then those are our answers to part D. And that concludes midterm 2 exam review worksheet. Those watching the recording, in the description, I'm going to make a detailed explanation of the confusions in regard to questions 3 and 4. So check that out. Thanks for watching. I'll stop the recording and answer questions now.